Hi friends, so today we are going to start with Math Question Bank 9, and today is a very important video where we are going to discuss about the Fourier series. I am Dr. Ganguly. Now I have made this video with only this particular problem because this problem is very important and it is often asked as a question in different settings. So let's do a simple example which will illustrate the Fourier series to you. And again, you can ask this question in different type of interview settings. It could be in interviews for STEM jobs, or it could be for those where you are trying to recruit PhD students, postdocs, or even master's degree students. Now, the Fourier series is of course very important in anything to do with signals and systems. So nowadays, if you are dealing with anything like wireless technology or any kind of system, you are likely to have some functions involved, and these functions can often be expressed in Fourier series if they are periodic function. So the question I have here is that find the Fourier series representation of this function. This is a typical step function, and you can see here that this function f of x, if we plot it with respect to x, it is 1 at certain point, then it becomes -1, then again it becomes 1, and so on. And this function has a period of 2 pi, so you see after 2 pi it essentially repeats itself. And one way to look at a function and check if it is periodic is that it should satisfy fx equals fx plus 2 pi. So here the period is 2 pi. If the period was some value t, then it would be fx plus t. So here we see that if we take any point x at a distance x from here, so we can see the function value at this particular point f of x will be same as the function value at fx plus 2 pi or x plus time period. So this is something to remember. Now, Fourier series are very important because many functions are periodic, especially functions where signals are involved as far as the electrical sciences are concerned. And in those cases, you can take Fourier series. Fourier series also has an advantage over Taylor series because the problems related to differentiation and all are not there in Fourier series. So let's look at this Fourier series of this particular function here as a simple example. Now let's define the Fourier series. Essentially, you can express the function f of x in terms of one constant part, that is a0 by 2, and two summations, one of them involving cos and the second one involving sine. So we can write this as n is 1 to infinity a n cos nx, and n is 1 to infinity b n sine nx. So you can see that this is essentially an infinite series, and therefore it goes on and on. But what often happens is that for most functions this is going to converge pretty quickly. Sometimes these terms are known as harmonics. So essentially the Fourier series expands the function out in terms of a constant value or a steady value and a summation of harmonic terms. So you can think about this as cos psi plus a term involving cos 2 psi, another term involving cos 3 psi, and so on. And here terms involving sine psi, sine 2 psi, sine 3 psi, and so on. So I'm just talking about psi because psi is something we use in some different nomenclature, but here of course we are referring to x here. Now if we look at these different coefficients, we can obtain these coefficients from integration. So a0 is 1 by pi minus pi to pi fx dx, an is 1 by pi minus pi to pi fx cos nx dx, and bn is 1 by pi minus pi to pi fx into sine nx dx. So these are the three key coefficients in the Fourier series, and essentially if we know the function f of x, we can calculate this. Now here I'm taking the integral limits from minus pi to pi, so that's something which you can do for the kind of problem we are dealing with. Some people like to take the limit from 0 to 2 pi and so on. So these are the two more popular limits which are out there in different books. So now what we are going to do is we are going to calculate these Fourier coefficients for the given function. So let's again look at the function here, and we can see that the integral from minus pi to pi, that would be this particular region of the function. So here there is negative pi, here there is pi, and of course you can see this particular function again repeats itself. So that's the periodicity of this function. So we can split this into two parts. We can write this integral as the term which is from negative pi to 0, that is this part, and here you can see the value of the function is minus 1, so I have put minus 1 here. The second part of the function is from 0 to pi, and here I have put 1 here, so we can easily write this as 1 by pi, and then I get this term here minus pi plus pi, and so this particular coefficient a0 comes out to be simply 0 value for this particular problem. Now let's look at the second coefficients, that is an, and I'm dealing with the simple coefficients first. So this coefficient also comes to 0, but let's see how that happens. So again the definition is given here, 1 by pi integral minus pi to pi fx cos nx dx, and so I split this into two parts. I keep the 1 by pi outside, and I have one integral from minus pi to 0, the second one from 0 to pi. And again remember, as far as the first integral is concerned, minus pi to 0, the value of the function is minus 1, so this simply becomes a negative sign. And in the second part the value of the function is plus 1, so simply it's a positive sign. And again I know the integral of cos x is sin x, and of course the integral of cos nx would be sin nx by n. So that's what we have here. The negative sign stays here, and I get this bound here minus pi to pi. The second integral also becomes sin nx by n, and this is also 0 to pi. Now if we look at the bounds of this function sin nx, we know that sine of 0 is simply 0, and we also know that sine of n pi is always 0. So essentially these terms are all 0. So a n also comes out to be 0, which means there is going to be no cosine part of this particular function concerned. Now let's come to the Fourier coefficient which is important for this problem and which is non-zero, and that is the term involving bn. And bn is given by this integral here, 1 by pi minus pi to pi fx sin nx dx, and again we split this integral into minus pi to 0 and 0 to pi part, and recall that the minus pi to 0 part was minus 1, so minus comes here, and 0 to pi part was plus 1, so plus 1 comes here. This is actually one of the simpler functions as far as integral is concerned compared to dealing with any other functions such as exponential, sinusoids, polynomials, and so on, because you simply have a 1 and minus 1 here. The little bit of complexity comes because you have to split this integral, and that's all, that is the complexity. So again now we know the integral of sine nx is going to be minus cos nx by n. So again the sign changes here, the sign changes here, the sign becomes cos, the sign becomes cos, and we divide this entire thing by n. Now of course we have to look at the bounds of this cos nx function between 0 and minus pi. So again the first term becomes cos 0. Cos 0 is simply 1 minus cos of n pi. Okay, so remember cos of minus n pi is same as cos of n pi. So this comes out here. Now the next term I can take the minus out of this bracket. I can put it here. So I would get a cos n pi minus 1 term. So this is the solution here. But I can simplify this because I know that cos n pi is minus 1 to the power n. And you can verify this particular fact using your calculator, that cos n pi actually keeps varying from negative 1 to 1. So for example, if n is 1, this is going to be negative 1. If n is 2, this becomes negative 1 square, which becomes 1, and so on. So I can write it in this form here, and then I can further simplify it because I can write this as 1 minus minus 1 to the power n. This becomes plus 1 here, and I have minus 1 to the power n. This 1 plus 1 gives us 2, and then these two values of minus 1 to the power n, there are two of them, so I get 2 minus 1 n to the power n pi. So that is the Fourier coefficient Bn. Now I go back to my starting definition or equation for the Fourier series. So this is something you must always commit to memory, that the Fourier series of the function is a0 by 2. The sigma n is 1 to infinity an cos nx, and sigma n is 1 to infinity bn sin nx. And now, having calculated a0, an, and bn, I can write a0 is 0, an is 0, and bn is 2 minus 2 to minus 1 to power n by n pi. So I can write this Fourier series in this form. The first two terms are simply 0, so I get the third term out there. Now, this actually is a pretty good definition of the Fourier series of this function, and you can see that this is very amenable to any kind of programming. So if you are asking this kind of question, it could be a question which takes about 30 minutes or even 45 minutes time, and could be put in a Zoom interview or something like that. And you can ask the student or the candidate to actually do this Fourier series calculation, and then to plot this particular Fourier series. They could also code this up in any language, maybe Python, Julia, Rust, or any language you can think of. So this is like a double problem. You test their capabilities on basic mathematics and also on computer programming. So let us now try to simplify this. We want to actually get a good picture of this. So if we take this and we expand this out, what I'm going to do is I'm going to substitute one by one. N is 1, I get this term. N is 2, I get this term here. Sine involving sine 2x. N is 3, I get this term. N is 4, I get this term. 5, 6, 7, and so on. Now, when you simply expand this out, one thing is going to become clear to you, that all the terms which involve the square here, or the fourth power or the sixth power and so on, that is all the even terms. These are going to be 0, because let's look at this term, for example, involving sine 2x. So here we see this minus 1 square is simply 1, so this is 2 minus 2, so this term is 0. Here we see that minus 1 to the power 4 is simply 1. So this again becomes 2 minus 2. So this term involving sine 4x is 0. Now we take this term here involving sine 6x. Again we see minus 1 to the power 6 is 1. So 2 minus 2 is going to be 0. So this term is 0. And we'll see that all the odd terms will be there, because let's say take the sine x term. Here minus 1 to the power 1 is simply minus 1. So this becomes 2 plus 2, or 4 by pi. Similarly, let's take the sine 3x term. This becomes minus 1 cube, that is minus 1. So 2 plus 2, that is 4 by 3 pi. Now this term here becomes minus 1 to the power 5, that is minus 1. So that is 2 plus 2 by 5 pi. This becomes 2 plus 2 by 7 pi, and so on. So essentially what happens in this Fourier series is that the even terms are decimated and the odd terms survive. So I can simply get rid of all the even terms, and now I know that the Fourier series is going to involve sine x, sine 3x, sine 5x, sine 7x, and so on. Now I can simplify all these particular values here involving 2, and then I can write simply 4 by pi, 4 by 3 pi, 4 by 5 pi, 4 by 7 pi, and I can get this series. So this is one more way of looking at the Fourier series solution. But I could actually still simplify this further, because I could take 4 by pi out of this summation series. So let's do that. Let's take 4 by pi out, and so the series becomes fx is 4 by pi sine x plus sine 3x by 3 plus sine 5x by 5 plus sine 7x by 7 plus sine 9x by 9, plus on and on it goes. So this is a series which never ends, so it goes on and on, my friends. So let's look at this function here. Now you can of course see this function, and you will realize that sine would be a good fit here, because you know you would go something like this here. The peak would be here and like that. Of course, one term solution would be too simple for it. It would go out of bounds and like that. So what I'm going to do is I can easily program this. So I actually created a simple solution in an Excel spreadsheet, and I'm going to show that to you in the next slide. So this is the Fourier series and how it works. So essentially, I have taken here the first term solution, one term solution, to the three term solution, five term solution, all the way to 15 term solution. So you can clearly see that when I have only one term, I get a sine function here. So what this thing tries to do is that it tries to fit a sinusoidal function through the step function, and as I keep more and more of the harmonics, I get a better and better match here. So this is something which the Fourier series is very good at, that it can even approximate a function which is discontinuous, which is not good in terms of derivatives and so on, and it can get us a pretty good approximation here. So again, in cases where you are looking at approximations, you can go for polynomials. In some cases you can go for Fourier series for periodic functions and so on. So generally, whenever a function is periodic, like for example in many rotor dynamics problems we have periodic functions, anything to do with rotating machinery, or even in many waves, which are the fundamental building blocks behind any kind of wireless transmission or any transmission system, you are going to be able to use Fourier series very much. And so wherever any kind of periodic functions are involved, you will find that that field is completely filled with Fourier series, and also its brother, or let us say its half brother, the Fourier transform. So that also I'm going to discuss in some video sometime soon. Now this problem is very amenable to programming, so like I have done here in an Excel spreadsheet, but you can also do it using any simple programming language. Now, of course, various different functions are out there for which you can be asked to find a Fourier series. If you check out Google, you will find many such representations of functions out there. But I think the unit step function is one of the simplest functions and one of the interesting functions, because it brings out certain features at which Fourier series is pretty good, that is dealing with functions which do not have good derivatives, which may not be continuous or differentiable in some cases, all those kind of problems which Taylor series would encounter in those functions are not encountered by the Fourier series. So that was the lecture for today as far as Fourier series questions are concerned, and I hope you will be able to get a good idea about Fourier series from this particular function. And I will leave some videos on the end screen which tie to some methods such as the harmonic balance methods. That's very important as far as rotor dynamics, helicopter dynamics, wind turbine dynamics problems are concerned. And if you feel that you do not know why people study trigonometry in high school and college, one of the reasons is of course that a lot of the world can be expressed in terms of sine and cosine. Remember that these are orthogonal functions. In one of my previous videos, I have showed the concept of orthogonality, and that is actually the basis about the derivation of the Fourier coefficients also. So do take a look at that. So I'll end this video now, and I will see you in a video sometime soon. See you then.